Okay, so we're gonna start with the second invited speaker session. And so now with us, we have Joanne Tu from Amazon AWS AI and also from UCSD. So Joanne has done some really great work in a number of areas, which includes tracking, detection, structure prediction, and most recently also on vision transformers. He's a recipient of the David Marr Prize Award in 2003 and also a recipient of the David Marr Prize Honorable Mention Award in 2015. And today he will give a talk on transformers for structural extraction. So please help me welcome Joanne.
Thank you so much, Gideus. Thank you, everyone. Really appreciate organizers to invite me to give a talk here, and also feels really great to come back to an in-person conference. So the title for my talk is Transformers for Structural Extraction. So I'll try to provide some of my biased views for transformers and also transformers for vision applications. The outline of the talk: transformers overview, 4 pieces of our recent works, 2 last year, CVPR ICCV, and 2 this year, CVPR 2022. A quick overview: visual perception. We have images viewed, and then we have our internal representation system and a perception system to perform some cognitive tasks, visual perception, reasoning these tasks. The vision community, computer vision community, has been largely inspired by David Marr's theory, going from retina, there's V1, V2, and there's dorsal pathway and the ventral pathway. And the cameras, in David Marr's theory, we have input image, and then there's primer sketch that performs basic feature extraction or edge extraction, and then with the grouping, then together with 2.5D sketch, then you basically have a 3D model, either as a non-parametric or parametric model. So David Marr lined out these theories. We have really benefit a lot from David Marr's theory. But on the other hand, the computer vision field, to some degree, has been following this strict stage-wise system. One of the caveats is that we have to rely almost on perfect feature extraction to start with. Then strictly step by step, we have some objective to achieve. For example, edge detection is one of the most celebrated tasks in computer vision. Given an image, we would perform edge detection. Computer vision field has tried really hard to refine the results of edge detection. Then suppose we have shapes to match, then typically there's template matching. So this is kind of a typical pipeline, but unfortunately, the structural extraction part has been focusing too much, relying too much on this stage-wise system. So of course, now transformers are taking over in both NLP, computer vision, and beyond. The strong kind of significance of transformers, this active kind of query and search thing, that was kind of to some degree unprecedented, especially to computer vision for our traditional way of thinking about problems. So this is just illustration of the standard transformers. So this type of transformer architecture potentially gives us semantic relationships between word tokens that are learned. Recently, prompting or fine-tuning these technologies allow us to extend transformers to domains beyond specific kind of things that are being trained. And also, it's generally applicable to different domains. So this inspired us to form things that are more general to computer vision. My biased view, to some degree, I feel like in addition to the so-called inductive bias, that in a sense, less inductive bias introduced by VIT type of or transformer-based visual architectures compared to CNN models, the true significance or a couple of two main significance of transformers that are bringing us. One is this general representation for vision, for bridging vision and language or beyond. Now we can better tokenize these representations, and language models can be almost to some degree seamlessly combined with the vision representations, which was a little bit unprecedented. Imagine if we have the CNN models, and then we have these language tokens. Traditionally, people have tried, but at least not as seamless as a transformer backbone. This is first. Secondly, another significance thing for people working in computer vision is the structural prediction for transformers, which was really very different for me. I'll go over those four works that probably summarize some of the advantages of vision transformers especially for structural prediction, which we really kind of have faced the difficulty with in perceptual grouping type of thing. Another thing, of course, is the seamless integration of encoder and decoder strategy. Okay, so first piece of work, line segment detection using transformers without edges. This was a CVPR paper last year. So some of you know our work, holistic edge detection with signing, and this shamelessly say that won David Marr Prize Honorable Mention Award 2015. So back then we were trying to push seeing models together with deep vision to make sense of the individual layers for edge detection. Then in the end, you're going to combine to produce something that's close or approaching human level performance. So this benefit a lot from the Berkeley benchmark, and our head is getting close to this human level performance on this data set. And also each dot here represents one single person, so we can see people are different, but to some degree, people are also consistent. So what's next? So in our head, we perform per pixel detection. For a lot of the downstream computer vision tasks, we need structures. What if we need lines, we need curves, we need polygons? If we would stop from here, then typically suppose these are per pixel classification for the edges. Then, typically we can perform edge thinning to extract these individual points on line segments to some degree, but they are still individual. Then a typical step is to perform half transform or edge linking to obtain your line segments. For example, you're going to vote for each point. You're going to vote in your parameter space, and enough votes will give you this line segment. But we all know there's advantage of half transform or like a ransack type of thing, but also their disadvantage. You have to organize your parameter space, and when the number of parameters increase, then it becomes difficult for us to do. So this is why I feel like the transformers, especially for structural extraction, really gives us an unprecedented paradigm that was not capable before. So these are previous state-of-the-art results using a CNN-based architectures by performing line edge detection, junction detection, and further with grouping. So our idea last year was trying to significantly simplify this paradigm using transformers. You can also consider trying to use a fast CNN type of model to perform line segment detection as a special object. The line segment can be horizontal, can be vertical. It is very kind of special type that has really elongated structure. So for example, we have short lines, we have really long horizontal lines, we can have very long vertical lines. So these are these anchors for your proposals, right? And for people who are familiar with fast CNN. But because of this, the degenerate structure as an object, if you blindly apply faster CNN, the results won't be satisfactory. But this also gives you a one-shot way of performing or obtaining edges, but not optimal, because the line segments are atypical. So in spite of Dieter or Detter, and also the recent transformer architectures performing, especially in terms of grouping or its potential power of performing grouping or relationship detection. So we propose this very simple architecture. And also by replacing this bounding box errors directly by point-wise errors. Basically, your objective function is just to minimize the endpoints of your predicted lines to your ground truth lines. So this is a very simple architecture, but you can skip these kind of intermediate stages of edge detection, junction point detection, grouping. Transformers really here gives you, and as I said, unprecedented the power of performing structural or geometric structure grouping detection all together. You can have a coarse to fine strategy as well. So this is a detailed kind of a thing. You have an image and you extract backbone seeing features. Now you can use VIT-based features as well. Then you have these queries of these potential line proposals, and almost like if these are the ambush that you've learned. They are sparsely, we visualize, they're sparsely kind of spread it on your image. And through these transformer attention mechanisms, in the end, you obtain line segments altogether. In addition, you also have these two co-relationships learned. So the key takeaway, so you can treat line segments as a special objects, but if you would directly treat objects using fast RCN type of, or even data type of thing for moment detection, the result won't be optimal. But here, if you treat them as structure, a geometric structure, and forget about your bounding box, and then you can extend this idea to further tasks, then there's really a wide open sky for vision computer vision tasks, downstream tasks. You can also engage multi-scale. So these are some illustrations. For example, one particular query for different images. You can see in the end, they land on slightly different places, but more or less like these are like animals, right? So you have these large mountains, you have tigers. Each tiger probably has its own territory. They will move, they will travel, but they're kind of limited to some degree to their territory. But on the other hand, the scope of territory is also pretty large, and unlike before, we have very limited kind of scope. These tigers are really strong, and they travel to a long distance to some degree. So these are some of the line segments for each particular query after layers of these self-attention, also cross-attention mechanism. So these are some of the powers. Again, as I said, compared to standard approaches, if you would blindly applying a fast RCN or data detector, you won't get good results. So if you would apply vanilla object detection, because there's this elongated structure. We had the state-of-art or near state-of-art results, but under very simplistic transformer-based architecture for structural extraction, especially geometric structure. So these are some of the comparisons. So in interest time, so I'll quickly skip that. You can see, so not only like you can have one-shot detection, also the potential structure, the relationships are implicitly carried in your transformer self-attention mechanisms. So conclusions, it's a general purpose machine and beyond the standard bounding box representation. And then you can really alleviate a lot of burdens in standard half transform or ransack algorithm under this transformer regression strategy. So second piece of work is called the code scale convolutional image transformers. Last year, ICCV. Last year, I was almost like a golden time for people developing VIT-based models, following the VIT architecture, and also BIT or DIT, I forgot, sorry. So we had a paper, ICCV. I think on ICCV, there were about 10 to 15 papers, all following VIT architectures. Our work has two kind of specialties back then, but now things start become a little bit trivial to some degree. So first, we had the depth-wise convolution now, which is widely accepted concept in transformers or even in CNN models. Then we have a attentional mechanism that generalized convolution to attention using relative position. This is also widely accepted concepts now. Basically, we can have a vectorized attention to significantly reduce the complexity. This is our backbone. And we have a serial block, to reduce the resolution and having a coarse to fine strategy. And also kind of a little bit special compared to the other formulation is we have a so-called co-attention or cross-attention, cross different skills. So we have three implementations having these different scale for implementation going in a cross-attention way. As I said, this is just one of the 15 or 20 papers last year along the line of VIT. There may be more. So we have some kind of comparative results back then with small models and medium-sized models. And also in terms of performance for object detection, our results are pretty competitive back then. And also compared to a swing and for the small and tiny models, our results are also stronger, but we didn't have a large model to train with because of the GPU limitations. So yeah, that's kind of the backbone thing that our lab engaged. And then this year, we have a paper called Instance Segmentation with the Master Supervised Polygonal Regression Transformers. Again, as I said, kind of there's two significance. One of the two significances of the transformer architecture for us is to perform structural or geometric structural extraction. As we can see, right, so VIT families like last year, especially swing, has shown improvement over CNNs, especially for object detection or instrument segmentation. But if our task is limited to these standard computer vision tasks, but probably there's not much, really a big, strong motivation for us to replace ConvNets with VIT models, because later on, FAIR also has ConvNets that shows almost like equivalent performance with swing type of models. Of course, the knowledge or experience learned from training these ConvNext or Conv type of thing from transformers as well. So it's not like a mere replication of standard ResNet or CNN transformer training, or some training. But nevertheless, if our tasks limited to standard computer vision downstream tasks, myself, I don't feel like there's really big motivation, but rather this multimodality fusion and also structural extraction and relationships beyond the just standard tasks. I think this is where transformers can really take off. So this is a paper, this time CVPR by Justin Lazar and Wei Jianxu. The idea is to perform polygon detection for instance, like in a vectorized way. So this is standard kind of pooling for mask instance segmentation. But if you directly use mask, for example, these are the individual masks, then per pixel confidence, right? So if you do a simple thresholding, you can have a binarized version for them. And then you can see artifacts will be present here because these pixels are obtained individually. And there's no topology, no geometric, explicit geometric structures enforced. You will have degenerate cases, especially for some medical instances where you really want to have to keep the integrity. And even you have these masses turn them into vector representations, you have this anti-silicene, all these artifacts. So the motivation is to obtain polygonal structures. There has been work doing this, but first you need to have polygon supervision. Second, these losses are hard to enforce. The reason is the following. Basically, if you represent a region using polygon, then you have a number of control points of 10 points, that let's say. Then in your training, if your purpose to directly minimize your training loss to match the ground truth polygon, then you have a so-called quotient space problem. Because the same polygon or very close same polygon, you can have very different sets of control points. They more or less represent similar mask, but if you would measure per pixel or no control point distance, the distance can be really large. And think about just a circle, right? So if you would place 4 points on, or let's say 10 points on the circle, you can have a systematic shift for these control points, and where they represent almost exactly same circle or disk, but nevertheless, the point distance is really large. So this quotient space problem also is problematic. So this motivates us to have a mask supervision, but trying to predict polygons directly. So these are some comparisons between mask supervision and mask prediction versus polygon supervision and polygon supervision. But we want to have mask supervision as like in standard mask RCN type of or instance segmentation formulation, but rather you predicting polygons without supervision. So the bridge can be done by using this differential rendering. For example, here, these are some control points for your polygon or polygonal detection or prediction. Then basically you can have a sign for the individual point over here, whether it's inside or outside. This is standard kind of sign, adding the distance function. So in the end, you have rasterized softmax to represent your mask with respect to your control points for the vectorized polygon representation. So given that, now suppose you have an input image, then you put to the backbone, CU models or VIT-based family. Here you have two supervision, ground truth labeling. One is the bounding box, another one is mask. So that's what we have. So now suppose, like a data or like in our line segment detection, you have these queries over here to predict for each instance, you have the control points. They're like ambush queries. So in the first layer, suppose you have 4 points you can obtain. So now based on these 4 control points, you obtain a polygon here. And our job is trying to minimize the difference between this polygon to our ground truth mask. Of course, there's disconnect, right? Because here the ground truth is per pixel. Here, these are the control points in the vector representation. So as I said, the bridge lies in this the beautiful differential rendering rasterization. So now if you turn this polygon into a soft rasterization, now they become per pixel. So you can minimize this per pixel difference between these generated softmax to the ground truth, but also, of course, to encourage these two masks to be aligned. So in the end, these forces will be turned into driving the control points, essentially through an equation type of thing. So that's the motivation. So now using a different in the general kind of split and differential rendering paradigm, you can use per pixel mask supervision and then to drive or turn things into a vector representation. So after that, and also we can take advantage of the transformer architecture by refining your queries. So now you have more control points to refine through this integrated architecture or seamless architecture. Then in the end, we can see that the loss is being minimized by matching this rasterized softmax from vector representation to our mask. This refinement is also kind of very convenient in transformer. So if we would perform this thing in a standard CNN architecture to perform per control point detection, we will face a lot of potential troubles. For myself, I probably just don't want to implement algorithm like this, given the potential kind of heavy kind of procedures and coding tasks to do. So this is kind of, so algorithm in the end is very simple. We're having a standard mask supervision, just like in standard mask RCN type of thing, but in the end, we obtain polygons directly without polygonal supervision. So we obtain state-of-the-art results or competitive results compared to mask-based supervision and compared to previous algorithm attempting to obtain polygons directly for the mask. I think we have a quite large improvement. And the algorithms are very simple and almost like a plug and play compared to some other methods. You don't need to introduce too big kind of change to the loss function. As you can see now, the masks are just are replaced by the polygons. And here, if you would think to introduce high-level shape pairs, all the things that the traditional vision research has engaged, I think you can do that. You can imagine to add even more constraints to your geometric structures here. So this opens a door to a feature extraction, geometric structure. Now here is instance space. So let me quickly summarize another work. It's called here CVPR text spotting transformers. Again, by taking the advantage of structural prediction and also multimodality. So the text spotting task is trying to perform detection of these not just bounding box, also in a way it's a polygon, and also trying to recognize these things together. So again, as I said, under a unified formulation of transformers, so you can push the polygon detection, and also you can push OCR in a single framework. For the details, you're welcome to go to the posters and also talk to my students and not me as well. So here, the gain or the advantage of using transformers is that you can deal with these texts of arbitrary orientation. So we achieve competitive results in this text spotting kind of thing, especially here. For example, if you would engage traditional text spotting using CNNs, there's a sequence of algorithms that you have to engage these bounding box detection, then heat map and grouping. In the end, trying to obtain these line control points and also to perform OCR. Again, as I said, the transformers here give us really an unprecedented unified framework to doing so. Yeah, I'll stop here. Thank you so much.
Thank you for the excellent talk. If anybody has any questions, again, please step up to the mics. Let's see. Any questions for the talk? Is it okay if we conclude just?
Sure.
Yeah, so since we're running out of time, I guess like we will stop the questions. But again, let's thank the speaker for the excellent talk. Thank you so much. Okay.